Good evening, my dear JEE 2026 aspirants, my dear class 12th as well as dropper students. Welcome to the next class of your electrostatics chapter. It's a big chapter, heavy weightage, lot of concepts, and so many things which you learn here are useful in so many other chapters. So it's time for electric dipoles, what kind of fields and energies they cause, potentials around them, and what happens if you take a dipole and place it in somebody's field, and what kind of torque and energy do they experience. All of this in today's lecture, where we are completing the syllabus. We are on to full speed already. Yep, and everyday class 12 standard syllabus at 8 o'clock and class 11 standard syllabus at 6 o'clock. Okay, so this is your Captain Shreyas, your physics master teacher. Quickly introduce yourself if you are new in the channel by putting up your name, your city, what you are aiming for, etc. If you're watching it recorded, it's okay, perfectly fine. You can put it up in the comments. All right. So let's begin with the class. And last lecture we had done, by the way, the playlists, everything are ready now. So, by the way, last lecture, guys, we had done electrical potential and electrical potential energy. It was a beautiful class. A lot of 11th standard concepts of work, power, energy also got revised during the session, and I had asked for some comments in the homework. Very good, Senthil, Telugu, Sriharan, Anyuban, Mohammed, and Desh. Well, very good, very good. Keep it up, guys. Proud of all of you. And if you continue like this, I'm pretty sure next year your name will be there instead of Daksh or Prakhar or Anubhav or Ketan or Sabyasachi or so many other students like Sohail, Aryan, Vipul and Manish and so many others who did exceptionally well in our JEE advanced examination. And Vedantu has a very good selection ratio. Out of all the students enrolled, almost 1 out of 3 students gets through the JEE advance. That's insane. 33% clearing JEE advance. I'm not talking about mains. In fact, the mains ratio is 1:1. One student gets selected out of 2 students. So that's crazy. Hi, Boo. Nice to see you back. Over here, hi, Ashwath. Hi, Snentil. Hi, Tharun. Hi, Suji, Moonlits. Welcome, welcome, Sanjuta, Sagar, everyone. Cupcake. Good evening, guys. So let's begin. What is a dipole? As the name suggests over here only, di means two. Di means two. Poles means polarities. Now, in case of electric charges, there is positive and negative. So two polarities, one positive and negative. So electric dipole means you have two charges equal and opposite separated by a small distance. That's called as an electric dipole. As simple as that. Okay. So an electric dipole is nothing but two equal and opposite charges, that is plus q and minus q, separated by a small distance. That is basically called as an electric dipole. There are many natural examples of electric dipole. Like most of our molecules, they have some kind of electron cloud shift towards the more electronegative atom or element. And for example, you have the molecule of HCl. The Cl has a delta negative charge and the H has a delta positive charge. Even for that matter, H2O, you have oxygen and 2 hydrogens. The oxygen has negative delta 2 times. This has 1 delta positive and 1 delta positive, negative positive, equal amounts. So, these are all polar, two polars being introduced over here, two polarities being introduced over here. So they are basically electric dipoles. Okay, most of the molecules around you, usually they will be electrically dipole or polar in nature. They will have two equal and opposite polarities. Is that right? Yes, definitely, Ibu. I'm pretty sure you will get it, and once you promise yourself, nothing going and no going back from there. Okay, yeah. So moving ahead to how the field looks like due to an electric dipole, which is very obvious kind of. So if you have a positive and negative charge, you will see that the positive charges always will emit the field lines and they have to terminate on the negative charge. So the electric field lines go like this, terminate on the negative, go like this, terminate on the negative. They will also go like this, like this, like this, like this. They keep on spreading. None of the places you will see the field lines ever intersect. That's how the field lines will look like. If you ask me how the electric potential lines will look like, they have to be perpendicular to that. So one thing is very obvious, and that is there will be a line like this. There will be an equipotential line like this. Remember, equipotential lines, we have discussed about it. They have to be definitely perpendicular to the field at every single place. So I have to make sure that I show it perpendicular at every single place. Then you will see that the field lines over here, that the field line, sorry, equipotential lines over here, they will look something like this. Then they will go like this. Then they will go like this, something like that, like this. Same thing over here. Everywhere the equipotential lines should be perpendicular to the electrical field lines. Everywhere they have to be perpendicular to the electrical field lines. So this is how the equipotential lines look like. This is how the equipotential equipotential lines look like. It looks like some alien staring into you. These are his angry eyes or something, isn't it? Yeah. I hope this is absolutely clear. Yes, Sandy, you can say so. Rama, sir, why they don't connect directly? Well, electric field lines never can intersect each other, Rama. Remember that. So that's why they can't just connect directly. So if there is one more field line, it will not pass over that same field. It will stay away from it. The next field line should stay more further away, because if it comes close, then it will intersect. So that's the reason why they will never cross each other's path, or they will not connect directly. Okay, there are bunch of field lines, and plus they are imaginary. There are infinite number of field lines that will come out of a charge and which will terminate also on a charge. Another interesting thing, that there is a reason why I have marked this particular line in pink. There is something special about it. Every point on this perpendicular bisector is equidistant from the positive and the negative charge. So the positive charge will give a positive potential, the negative charge will give an equal amount of negative potential. So the total potential will cancel out each other, and on that pink line, the net potential will be zero. Do you guys agree with it? So that pink line is the locus, it's the collection, it's the set of all those points which is equidistant from positive and negative charge, because of which the net potential is zero. Is this absolutely clear? Also, you will notice one thing. When you talk about these lines over here, closer towards the positive charge, the potentials will be on the positive side. So we will be positive, because more positive than negative. But if you consider these equipotential lines, they will be definitely negative potentials, because you're closer to the negative as compared to the positive charge. Is this also understood, everyone? Give me a thumbs up quickly. Yeah. Yeah, current electricity will come after this. Gauss law is there, applications are there, so many things are there, capacitor is there. After that, current electricity and all of that will come. Okay, don't worry. So if you are done till this point, then we'll go ahead. Okay. Yes, sir, I understood what is a dipole. There are live examples of it, how the field lines look like and how the equipotential lines look like. But sir, are there any formulas related to an electric dipole? 100%. So many formulas are there. So let's get to it one by one. So if you have a positive charge and a equal amount of negative charge, and there is some kind of separation between them, and let's say the separation between them, I call it as L, then there is a dipole moment. There is a dipole moment which goes from the negative to the positive. Mind it, field goes from positive to negative, but dipole moment goes always from negative to positive. The symbol for dipole moment, which is a parameter to measure how strong the electric dipole is, has a symbol of P. It's a vector quantity. So the dipoles, the electric dipoles strength is measured is measured by the term or the physical quantity called as the dipole moment. Dipole moment. Next important thing, it's a vector quantity always going from negative to the positive charge. Very, very important. Many people make a mistake in a hurry because you link it with the electric field. Yes, electric field goes from positive to negative. Dipole moment goes from negative to positive. Next important thing, what is the formula for it? The formula for dipole moment, the magnitude, is just given by any one of the charge. Okay, any one of the charge. Let's say I take Q, take the magnitude of it, okay, magnitude of it, and multiply it with the length. Multiplied with the length. This length is nothing but the separation between the charges. Separation between the charges. Now, in your NCERT and in many books, I have seen that they use this length as 2L. Now, I understand why they do it, because they want to use it in the derivations. They take the midpoint and then the convenience factor comes in. But why do you want to say the distance between two things is 2L and then confuse the students, and then you have to substitute L or 2L? What is the separation? Why would you do that? Why will you say the distance between two cities is 2x and x is 5? I mean, just tell, no, the distance is 10. Why do you want to say it is 2x and x is 5? Why do you want to confuse people? So we will not use 2x, 2a, 2l, etc., which causes a lot of confusion. They use it for their own convenience, only for the sake of derivation, but we are not bothered about a short-term benefit. The long-term benefit in the exam is you should not be confused. So that's why we just stick to L. Is that okay? Yeah. These are for droppers also, FLGR, and also for your class 12th freshers, both of them. Okay. So this is the magnitude of the electric dipole moment. P is Q into L. P is nothing but charge into the length. I hope this is absolutely clear. Okay, perfect. Okay. Now that you have understood it till here, what could be the unit of the dipole moment? This is nothing but in coulomb. Charge is nothing but in coulomb. Length is obviously going to be in meter. Length is obviously going to be in meter. So the unit, so the SI unit, the SI unit of the dipole moment is nothing but coulomb meter, which you can also write it as in short form capital C but small m, because meter symbol is small m. Coulomb is the name of the scientist, that's why you use capital C. Like Newton, you don't use small n. Okay, you use capital N whenever the unit stands for the name of a scientist. Meter is nobody's name, so it is just a common name, so that's why you use M. And because many people will get confused with centimeter, that's why we put that dot or that hyphen, because you should not confuse with the word centimeter. This is capital C. In centimeter, that C is small c. Okay, and there usually you do not put the dash or dot or anything. This dot and dash is just to explicitly be clear that hey, the unit is not centimeter, it's coulomb meter. Okay, so that C also is capital alphabet. Okay, fair enough. So if dipole moment is a vector quantity, unit coulomb meter, can we also add dipole moments of different things using the laws of vectors? Why not? Imagine, imagine, consider the molecule of water, H2O, H2O, two hydrogens and one oxygen, versus consider the molecule of CO2, two oxygens and one carbon. Okay, just consider these two molecules. Now we both know that the oxygen being more electronegative over here, it gets some negative charge over here. This will get some small shift of electron cloud, so this will be negatively charged. It will suck that electrons from the hydrogen, so hydrogen will develop an equal amount of positive charge in water molecule. It will suck that electrons from the carbon, so this will develop some positive charge right over here. Is that right? So these are the polarities or the charges which are developed, okay, because of the electron cloud shifting. You might have learned this in chemistry. How many of you remember this? Okay. Yeah. But for scientist name, we use small letter. No. We always use like 5. You never say Newton. You never say Newton. That is wrong. You say Newton. N capital, like this. Okay. Never will you use small alphabets for a scientist name. Like if it is my name, imagine, will you ever write Shreyas like this? Even your name? Never, right? You always write S capital. Whichever is your first alphabet, you always write that capital. Remember, that is the rule. Okay. All right. Fair enough, Hema. Now, can you see that there are two dipoles being formed, and dipole moments always go from negative to positive. So this negative to this positive is one dipole. This negative to this positive is another dipole. This negative to this positive is a dipole. And this negative to this positive is also a dipole. Okay. Now the best part is that both these dipoles are same in amount, P1 and P1. Let's say I call this P2 and P2. What happens is, if you consider the vector addition of this P1 and this P1 using parallelogram law, triangle law, whichever law you want to use. Let's say over here I use parallelogram law. I add them, I will get their net vector resultant. This is your net resultant over here. Here also, if I do the same thing, because one vector is here and the other vector is here, they will end up cancelling out each other. So the net is going to be 0 because they end up cancelling out each other. So this one over here, the net resultant that you are seeing for a water molecule, the net resultant dipole moment that you are seeing for the water molecule, this is basically your net dipole moment. This is your net dipole moment of your H2O molecule, which is definitely non-zero. Such a molecule is said to be a polar molecule. What is it said? It is said to be a polar molecule. It is said to be a polar molecule. It has some polarity. Whereas here, you can see the net dipole moment is gone. It's not there. So they are basically non-polar in nature. It's non-polar in nature. It's non-polar in nature. Is this absolutely clear? Because they're cancelling out each other. So over here, I can just say that the net dipole moment is 0. It's not having any net polarity. Clear till this point, everyone? How this is used for measuring the dipole moments and how it can be also related to chemistry and all of that. Everyone? So dipole moment means moving system? No. Dipole moment means that if you have two charges and there is some separation, yes, those two charges together, they are going to produce some kind of moment of force, which is basically torque, when placed near some other field and all of that. So that will come later of later part of this lecture. But for now, when you have two charges at the same place, then it will not rotate or anything. But the moment you separate them and you place it in somebody's field, zoop, it will rotate. Moment. So that moment of force, that is the concept of rotation. Every physical quantity comes with a prefix of moment of that. Moment of momentum is called angular momentum. Moment of force is called torque. Moment of inertia, right? So all these rotational quantities usually start with that word of moment. So this dipole moment means you can think that moment you take these charges and place it somewhere in some external field, they will start moving and they will start rotating in a way. So that's the reason for that. Okay, great. So let's solve a question on this. Three charges are placed at the vertices of an equilateral triangle. Can you figure out what's the dipole moment of the system? So since it's an equilateral triangle, let's start with an equilateral triangle out here. And the length of that side is given to be, let's say, A, I believe, because I can see A in the options. So A is there over here. Okay, and the charges are as follows. One of the charge is, let's say, positive Q, other charge is negative Q, and here you have, no, this is also positive Q, and this is negative 2Q. Now, initially, you might not look at any dipole moment, or you might not see any dipole moment as of now, but there is. Justice Seeker, thank you. Glad you are moving charges, magnetism, EMI from my lecture, scored 70 plus and got 180 in my school mains mock, which usually consists of mains level questions. Wow, that is so cool. Keep it up. Hopefully, you improve to 90 plus. I'm pretty sure Justice it is possible. Okay, it's not that difficult. We have a lot of time. Yeah, for JEE 2026, right? So one thing I notice is that this negative 2Q charge, I can write it as a negative Q over here and negative Q over here separately. Deliberately, I did it so that now I start seeing negative to positive is a dipole. This negative to positive is also a dipole. By design, the manner in which the question has been framed, charges are same, distances are same. So if this is dipole moment 1, this is also dipole moment 1. Same charge, same distance. How much is that dipole moment 1? It is nothing but any one of the charge. You take the magnitude of it and multiply it by the separation between them. So any one of the charge magnitude is Q, either this or this. I have just split the negative 2Q, one negative for this guy, one negative for this guy. So they become two independent dipoles. And the separation between them is A. So any dipole moment here or here is Q into A. That's not the final dipole moment. The final dipole moment will be a vector addition of both of them. And that vector addition should go like this over here. So this is the net dipole moment. And to figure that out, no, I will not use parallelogram or triangle law. I direct have a formula. So when I have two vectors and I know the angle between them, in this case 60 degree because it is equilateral, let me use our formula. The resultant is square root of first vector's magnitude plus second vector's magnitude plus 2 times first vector, second vector into cos of the angle between. As you can see, P1 square, this is also P1 only. P1 square, P1 square, P1 square is common. So if I take it like this, P1 square, here 1, here 1, here 2, cos 60 is basically half. That's what is left. And yes, do not forget that everything is under the root. I can take the liberty of shifting P1 outside the root. So P1 square's root will just become P1. And inside the root, I'm just left with 1 plus 1 plus 1, 1 plus 1 plus 1, which is basically root 3. So this will be root 3. And what the hell is P1? P1 is QA. So just put Q and A over here. That's it. So that is your net dipole moment. QA root 3. QA root 3. Yes, QA root 3, which is option A. Option A is the right answer. Option A is the right answer. Everyone got it? How we did it? Yep. Perfecto. Perfecto. Amazing. Right. So no matter how many charges you have, you can always use vector addition. Whatever rules you studied back there in 11th standard, you can still use it right over here. No denying that fact. Okay. Cool. So let's go now to the main agenda, which is finding the field, finding the potential, and mainly the problems on these fields and potentials due to a dipole. Okay. Now I'll tell you what. Okay. So let me just get this over here. Okay, I am interested in figuring out what is the field due to a dipole around it. I am interested in finding out the field due to a dipole around it. Also, the electric potential due to a dipole around it. You might be wondering, how do I do that? See, first of all, let's understand one thing. This is our positive charge. Let's say this is our negative charge. There is some separation between them. Okay. Now, if you extend that same line of separation between the two charges like this particular line has a particular name. It is called as the axial line. What is it called? It is called as the axial line. Similarly, if you draw a perpendicular bisector to it, then that line is called as the equatorial line. Equatorial line. This is the axis of the dipole. This is the equator of the dipole. Perpendicular bisector is the equator. The line passing through both the charges is called as the axis of the dipole or the axial line of the dipole, any one of them. Okay, fair enough. Once that nomenclature is clear, let's understand how the field lines were looking like. So let me just draw the field lines. Say, for example, it goes from the positive charge. It will go like this. It will be perpendicular over here and it will come back over like this. This is how the field lines were looking like. Many more field lines are there. I'm just showing a few of them. From the positive, they will come like this. On to the negative, they will end over here like this. Now just imagine, I want to find the electric field at any location. Imagine this was the electric field line. I want to find the electric field at any location around this place. I want to find the electric field at any location around this particular place. How do I find it? If I want to find the electric field at any location around this place, what I will do is observe carefully. Okay, I will first find due to the negative charge and due to the positive charge at any point, how much is the electric field, and then I will add them vectorially, as simple as that. Okay, so let's say the point that I have chosen, where I want to find the field is over here. So that point from the center of the dipole is at a distance of r and the angular position is theta. So this r is basically usually much larger than the length of the dipole. This assumption makes that dipole short. This assumption makes the dipole short. Why short? Think about it. If your negative and positive is here and you are very far away, for this distance, this dipole is very small. But your negative and positive is here and you are here. So then, I mean, it's not a short dipole, the distances are measurable, comparable. So when I say short dipole means that the distance between the two charges is very small as compared to the place where I want to locate the electric field. So this R also stands for the distance from the dipole. The distance from the dipole. Distance from the dipole. Next important thing, theta. Theta is basically the angular position. Angular position. angular position. Okay, angular position. Okay, all right. And our dipole moment is right over here. So I'll just put P vector like this from negative to positive. It's the angle measured with respect to the dipole wherever I am situated. Okay. Now observe carefully. Till this point, everything is clear. Imagine I first figure out, due to the positive charge at this particular point, what is the electric field? Okay, it is over here. Agreed? This will be the electric field due to the positive charge like this. Similarly, due to the negative charge at this point, how much will be the electric field? Because it's a negative charge, it has to be attractive field. So it will be somewhat like this. It will be somewhat like this. And let's say I call it E negative. These are the only two charges creating the field. If I take the vector sum of both of them, it will come like this, exactly along the tangent of the electric field line. This will be basically the net electric field. This will be basically how much? The net electric field. So the net electric field is nothing but a vector sum of the electric field due to the positive charge and the electric field due to the negative charge. It's just a vector sum of them. Now this E plus, if this distance is, let's say, R plus, and if this distance, let's say, is R minus, distance from negative charge, distance from positive charge, and all of that, we know that E plus magnitude wise will be nothing but Q is Q only, divided by R plus square. Similarly, E negative field, the electric field due to the negative charge, will be K into Q is the charge causing that field, divided by R negative square. Now, also remember there is some angle between them and all of that. So you use geometry, you use a lot of approximations and all of that. So after using all those approximations, you get the final answer. But you get the point, it is quite tedious, not needed for us. But you know, this is some vector, this is a vector. There are angles involved over here. There will be some approximations involved as well because it's a short dipole. And the moment it is a short dipole, understand the distance where you are at is very, very far as compared to the other distances. So it's very, very far. It's very, very far as compared to the dipole's length. So using those approximations, you get the final answer. So what is the final answer that you get? That is the most important thing. So let's get to that thing right over here. Okay. So first of all, the electric field that you get, the electric field magnitude that you get over here is K into P. P is the dipole moment. K into P, which is the dipole moment, into root of 3 cos square theta plus 1. 3 cos square theta plus 1. The whole thing divided by basically R cube. That is the field at any location due to a short dipole at some angular position. Theta can change anywhere, accordingly it will change. Also, this electric field, if you see, it is going to make some angle over here. It's going to make some angle with our position vector. You can see that angle is there. Let's say I call it alpha. So alpha is the angle by the field with respect to the position vector. That angle, tan, if you take, comes out as, if you do tan theta this theta, tan of theta, the whole thing divided by 2. It's not tan of theta by 2. You take tan theta divided by 2, that becomes tan of alpha. So these are the two major formulas that you are going to need. These are the two major formulas which are you are going to need for the electric field due to a short dipole. The manner in which it is derived is you find the field due to individual charges, positive and negative, and you do some approximations. And after you do the approximations and you add them vectorially, you get these two answers. One is magnitude, second one is direction. I am very good. Hi Vasuki, hi Sarvana, hi Kevin. Welcome. Hi Suji. Good evening, my dear students. Okay? Fair enough. Fine, sir. Can you tell me an example of this? Let's say an example on this. Say we have charges of plus minus, let's say 2 microcoulomb separated by 3 micrometer, okay? Find the field due to this dipole at a distance of 3 millimeter, making 60 degrees with the axis of the dipole. Let's understand it. Very interesting question. So we have a dipole over here whose dipole moment, let's say, is like this. So you are at some distance making angle 60 degrees with the axis. So making angle 60 degrees with the axis. So this is your distance over here, and this is exactly the place you want to find how much is that electric field. So let's try to find it. Okay, because the electric field is going to go like this, positive to negative. So let's find out the electric field. First, let's write down the formula. The formula as shown over here, Kp under root 3 cos square theta plus 1 by r cube. So let's put it. Kp root 3 cos square theta plus 1 whole thing divided by r cube. What is K? K is Coulomb constant 1 by 4 pi epsilon naught. So it will be 9 into 10 to the power 9. What is a dipole moment? We all know dipole moment is charge multiplied by separation. The charge is 2 micro. The length of separation is 3 micro. So it will become 6 micro into micro. Micro is 10 to the power minus 6. So it will become 6 into 10 to the power minus 12. 2 3 is 6. Micro is 10 to the power minus 6. So you square it, it will become minus 12. 10 power. So 6 into 10 to the power minus 12. This, remember, is Coulomb meter. This is Coulomb meter. Okay. Root of 3 cos square theta. So it will be cos square 60 plus 1. Whole thing divided by r cube. What is r? The distance, 3 millimeter. So millimeter is 10 to the power minus 3, but you have to cube it. So do not forget that. Okay. So we have 9 multiplied by 6. 9 and minus 12 will become 10 to the power minus 3. 3 cube will become 27. And we have 10 to the power minus 3's cube. So minus 9. This will become cos 60 is half. So square of it will become 1 by 4. So it will become 3 by 4 plus 1. Okay, 3 by 4 plus 1. So what will this become? Observe carefully now. 9 will go with 27 3 times. 3 will go with 6 2 times, leave it. This will completely go over here. This will become -6. So if I take it on the top, this will become 10 to the power plus 6, and 2 is also there. This 2 is also there. And here we will have 3 plus 4, 3 plus 4, and root of 4, which is basically 2 after taking LCM. So 2 will cancel, and I'm left with root of 7 into 10 to the power 6 newtons per coulomb. That is the electric field. Root 7 into 10 to the power 6. Okay. I hope this is absolutely clear. Hi Noshat. Good evening, Radhika. Yes. What is the dipole of the same charges? Meaning, dipole of the same charges is meaningless because dipole always is of equal and opposite charges. Dipole is defined two polarities, different, equal but opposite. You will never have dipole of similar charges in sign. Okay, Rama? Negative, negative, positive, positive can't make a dipole. Only positive and negative, or negative and positive. So that's how you find this out. Perfect. So I understood, sir, what is the meaning of it. Now, if at all they asked, I know they have not asked over here, but chumma, let's say for example's sake, had they asked what is the direction? They have not asked here, but obviously question can come. Direction. So understand what it means. This dipole with this position vector will make some angle over here. Let's say that is alpha. So if you measure that tan of alpha, that will be tan of theta whole thing by 2. Tan theta means tan 60 by 2. Tan 60 means root 3. So root 3 by 2. So that is basically tan alpha. So alpha will be tan inverse of root 3 by 2, which is an unknown angle. Okay, it is not cos or sine, it is tan. So I don't know whose tan is the root 3 by 2. So just leave it like that. So if the question says what is the angle with the position vector, this is the answer. But if the question says what is the angle of the electric field, what is the angle of electric field with the axis? So then the answer will be slightly different, guys. Be careful about it. So the angle of the electric field with the axis of the dipole, if that kind of question comes, be careful, guys. That will be not only this alpha, but also this theta. Yes, so it will be not only this alpha, but it will also be the theta value. And theta over here is 60 degree, and alpha over here, we just figured it out. It was tan inverse of root 3 by 2. So that is the total angle with the axis. And do not forget that this is your axis of the dipole. So with the axis, not only this 60, but also this tan inverse root 3 by 2. Okay. All right. I hope this is absolutely clear. Yes. Lazy, that is because of the offer, my dear kid. So, I think I had mentioned it on Friday also. Please don't buy any kind of batch now because there is an offer going to run. So it's just about the entry which came. So because of which the price was reduced. Otherwise, you know that when that entry is not going to be there and that was the final entry. So the prices of any kind of batch is going to come back to its usual standard value. Okay. So don't worry about it. Just continue. All right. It was just like when you buy a shoe, there is Diwali sale, or when you have a new product launch, there is a sale. So it is exactly like that. Okay. Is solving all JEE mains and advanced POK enough for getting good marks in JEE or not? Definitely not. Okay, it is definitely not enough. All right. So you need to go more beyond than that. Just solving PYQs is not going to help you get good score in JEE. Okay, that's a common myth many students have. All right. Now let's go to the electric dipoles potential. Potential due to that dipole. So again, coming back over here. Oops. This was our positive charge. This was our negative charge. And we all know that if you go anywhere on this line, you are equidistant. So anywhere on this line, the potential will be 0. the potential will be 0, but somewhere here or maybe like this. Here the potentials are going to be negative, whereas on this side the potentials are going to be positive. So these are basically your equipotential lines. Equipotential lines. Also, you can mention on the perpendicular bisector, that is basically the equator, isn't it, guys? This line is also the equator of the dipole. I had mentioned this nomenclature just some time back over here. What is the meaning of equator and axis and all of that? So this is axis, this is the equator. Yes. So basically on the perpendicular bisector or the equator, the potential, the electric potential is basically a big fat 0. This is very, very important. Electric potential is a big fat 0. Okay. This line over here is obviously the axis. This is the axis of the dipole. This is the axis of the dipole. This is the axis of the dipole. Now I want to find what is the electric potential due to this dipole at any given point. So let's see how that is done. Again, the logic is very, very similar. The logic is very, very similar, guys. What you do is you consider any random point. Let's say again, chumma some random point over here or here. Let's say it's like this. It will have some position vector. It will have some position vector. This is the position. This is basically the angle which it makes. Let's say it is theta. That point where you want to measure the potential will be at some distance from the positive charge. You can call it R positive, and it will be at some distance from the negative charge. It will be at some other distance from the negative charge. You can call it R negative. So now if I want to find the potential at this point, the electric, the electric potential at a distance r, which is much larger than the length of the dipole itself, this is the dipole's length itself, which is why it will become a short dipole, at angular position, at an angular position of theta, is just the scalar addition of potential due to the positive charge and the potential due to the negative charge. They are scalar quantities, so just do scalar addition. You don't have to do vector addition, which we did in electrical field. To find the net electric field, we had to do vector addition over here. So this over here is a vector addition, vector sum to find the resultant, But potential being a scalar quantity, you don't have to do vector addition, which is a good thing. You just have to do scalar addition. And the positive charge will give a potential of K Q divided by R positive, whereas the potential due to the negative charge will be K negative charge divided by R negative. Use geometrical approximations of short dipole and other, whatever geometry, trigonometry you want. After solving this and using all the approximations, the answer that you get is very important. K, which is Coulomb constant, into P, which is electric dipole moment, and into you have over here cos of theta, whole thing divided by r square, not r cube. Here you have r square, guys. So this is the electric potential at any location due to a short dipole. You can put it to a test. When you are on the equator, think about it. This point will be making an angle of 90 degree with the axis. So if you take cos of 90, it will be 0. So the potential should come out to be 0, which is exactly the case. Make sense? So, theta will be 90 at the equator. So everywhere cos 90 will be 0. So potential is 0, which makes sense that the formula is working. This is just to check whether our formula is working correctly or not. So very important thing that if you consider any location, this is r and this is theta. For the equator, the angle that you will be using is plus or minus 90 degree, and for the axis theta will be either 0 degree or basically 180 degrees. 0 degree if you are here and 180 degree if you are here. Okay, so sine 0 is 0, cos 180, sorry, sine 180 is also 0. So those trigonometric ratios you can use for axis and for equator, maybe at times. Okay, so what are the different things that we have learned? Due to a dipole, how the field and the potential lines look like. So if we want to find, the field at any location, use this formula. Okay, and if you want to find the potential at any point, then basically use exactly this particular formula. So in our previous question, which we just did, say for example, if we had to find the potential at that location, let's say we had to find the potential at that same place, instead of find the field, it said find the potential due to this dipole at that same distance at 60 degrees, then our answer would look like this. Potential will be k p cos theta by r square. K is 9 into 10 to the power 9. P, which is dipole moment, we got it already, 6 into 10 to the power negative 12 into cos of 60 degree directly, whole thing divided by, here you will have r square. R is basically 3 millimeter. So 3 into 10 to the power minus 3 meters square it. Okay, so what happens? This 9 into 6 as it is into 9 and negative 12 will make it minus 3. Cos 60 is basically half. Whole thing divided by 3 square is 9 and minus 3 square is minus 6. 9 cancels, 6 and 2 cancels, becomes 3. This minus 3 and minus 6 will become 10 to the power minus 3. So this will become 3 into 10 to the power 3 volts. So the answer for the potential is 3000 volts. So the potential at that place is 3000 volts. Is that clear? Everyone? Lazy, it is not possible, my dear. Okay. Hi, Divya. Welcome back. Nice to see you all here. Yes, welcome, guys. And hopefully you guys got this question. This is direct application based question. So a lot of people ask, sir, how do I remember formulas? Solve these kind of questions. It looks simple, right? But this is the exact kind of question. When you solve 2, 3, 4, 5 questions, then this formula will get stuck in your head. You should just know how to use it. Next, what you do, let's say, sir, where to find such questions? No problem. Get the same question. Imagine potential is given and you have to find distance. Imagine distance and potential is given, you have to find the angle. Use the same question. You already know what answer you should get. You should get the answer as 60 degree or you should get the distance as 3 millimeter. Just solve the question in the reverse. Whatever is given, you make it asked. Whatever is asked, make it given. Just play around with it. 3, 4 times, 5 times you do it, 100% you are going to remember it. And do this over a period of time. It's going to get stuck. Very few times you will need revision. Got my point? Okay. So we have done electric field and potential due to a dipole. Now it's time to see some questions on your screen. If EA is the electric field on the axial line and EE is the field on the equatorial line, at the same distance, then compare them. Very, very straightforward. Very, very straightforward. Okay, Swati, I have to go from the basics, and I know in the live I might be very average paced. Okay, because I have to make sure that everybody understands, be it a slow paced learner or a fast paced learner. So maybe in the recorded, you can speed it up at 1.5 or 2x. Is that okay, Swati? All right. All right. So how the formula is coming, Tarun, the via the your approximations. You have to use trigonometry over there. Pythagoras also you can use. Binomial approximation is also sometimes involved. All of that. So it's there in NCERT, but not needed. And by the way, I have also done the derivation separately. You can just check NCERT line by line. You can see the entire derivation. I have done it. It's not needed. Okay. So how do we do it? Quickly, guys. Electric field on the axis theta is basically 0. So the electric field on the axis will be k p root of 3 cos square 0 plus 1 by r cube. So this will be k p. Cos 0 is 1. 3 plus 1 is basically 4 by r cube. So it will be basically 2 kp by r cube. Now let's go to the equator. So if you are talking about the equator, theta will be 90 degree, plus minus 90 degree. So it will be kp 3 cos 90 plus 1 by r cube. So kp cos 90 is 0, so it will be just root of 1. Root of 1 is 1, so it is just kp by r cube. As you can see directly from here, electric field on the axis is obviously, if you take electric field on the equator, it is exactly 2 times. So if you take this and multiply by 2, you will get field on the axis. So EA is 2 times of EE, which is option B for IIT Bombay. Now this particular result, it's better you remember it. And it's very easy to also understand why axis is double of the equator. You just go with the diagram, guys. Things will be very obvious. Just look over here, or maybe just over here also, or here also. If you're near the axis, the field lines are too many in number. They are crowded, but at the equator, they are very, very far away from each other. In fact, this diagram makes it even more obvious. The red ones are the field lines. See, when you're at the axis, the field lines are plenty in number. When you go on the equator, see, they start spacing out. So when the density is more, the field is strong. When the density is very less, the field is very weak. So that's why on the equator it is 1, and on the axis it is 2 times. So double. Okay, that's how you can remember it. 1:2 is the ratio, 2 being the larger one, which is on the axis. Is that okay? Perfect. Let's go to the next one on your screen. This is a good question. For a short dipole, which is at the origin, the dipole moment P is along the x-axis. You can see the dipole moment P is along the x-axis. The potential in the field at point A is V0 and E0. Then what is the potential and field at B on the y-axis? Very good question. Okay. So Guruvar, in that previous question, the thing was, once you have considered the axis, once you have considered the equator, how do you compare the fields? So when you are on the axis versus the equator, like I just mentioned over here, if you are on the axis, the angle which you make, theta, will be 0 or 180. But when you are on the equator, it will be 90 degrees. So I have just used this formula, which I have obtained over here. Kp root 3 cos square theta plus 1 by r cube. First time I put theta for axis as 0. Second time for equator, I have put theta as 90 degree. So I have got the fields both the times. I have just got the fields both the times, one at the axis, one at the equator. Once I get that number, it is obvious that this guy is the double of this guy. So at the axis, it is higher because the field lines are just originating. They are more in number. But when you go to the equator, they are far away. The density will reduce. Last lecture, I had explained this last concept, how When field lines are close, it is strong. When field lines are far, the field strength is weak. Okay, that's the previous concept. Is that okay now? All right, let's see if you guys can figure this bit out now. Guru, I hope this is absolutely clear. Yes, Vivek. All right, let's see if you guys can figure this out. First of all, over here, if I try to find the field at point A, due to this dipole which is kept at the origin, understand this point A happens to be the axial point, and on the axis, the value of the angle made for that particular position, observe it carefully, it will be 0 degree, isn't it? On the axis, the angle which you make with the dipole, it will be obviously 0 degree. If you are here 30 degree, 40 degree, 50 degree, 90 degree. So as you come here, it is 0 degree. Okay, so let's use electric field at point A will be Kp root 3 cos square 0 plus 1 divided by r cube. So cos 0 is 1. So it will become Kp 3 plus 1 by r cube. 3 plus 1 is 4. Root of it is 2. So 2 Kp divided by r cube. Similarly, potential at point A, it will be nothing but Kp cos 0 divided by r square. Cos 0 is 1. So it will become Kp by r square. That is at point A. Now consider point B. If you notice point B, it is obviously on the perpendicular bisector. So it is 100% the equator. And for an equator, the angle which it makes with the dipole is 100% 90 degrees. Or on the other side, minus 90. So let's talk about the potential first. Potential is Kp cos 90 divided by r square. Obviously, cos 90 is 0. So potential must be 0. So 0 is there here and here. So C option and A option automatically gets eliminated. Is that obvious now? C option and A option gets eliminated. Either it is B or D. Now what about field at point B? It is K, P. Sorry, this R was not R. This was 2R because I think the distance is 2R. Anyways, it is 0. So Kp and then you have root of 3 cos square 90 plus 1 whole thing divided by 2r whole cube. Okay, this is for the field. Now what will this become? Kp cos 90 is 0. So 0 plus 1 is just 1 divided by 2 cube is 8 by r cube. Now what is this, guys? Kp 1 by 8 r cube. If you compare it with this, I can write it like that. 2 times Kp by r cube and then I'll put 16 because I want to get 1 by 8. 1 by 8 is also 2 by 16, which is also 4 by 32 and all of that. The reason why I did it is because I can clearly see that this 2, this k, this p divided by r cube is nothing but the original field. So that is nothing but EA, and just you have to divide it with 16. So EA by 16, that's option D. So hence option D is the right answer. Very straightforward. Yes, Vivek, that is absolutely correct. Perfect. Option D is the right answer. So I just did a manipulation. Root 1 is 1, 1 by 8 is 2 by 16. Why I did it? Because I knew that I have this number 2 on the numerator side. I wanted the 2 kp. So to get it 2 kp, I have to divide it also by 2 to balance the equality. So now I can clearly see this whole thing is EA. So I substituted that EA. So EA by 16 is the electric field. Right? Perfect. Moving on to the next one. The electric field due to a dipole at a distance r from its center in the axial position is E. The dipole is rotated through an angle of 90 degrees about its perpendicular axis. The electric field at the same point will be, guys, this is direct now. Now you should be able to give it to me very fast within 10 seconds or 15 seconds. Think carefully. You have electric field due to a dipole at a distance r in its axial position. So the axial position means somewhere over here. So at this place, the electric field is E. You have rotated the dipole now by 90 degrees. So if you rotate it like this, if you rotate that particular dipole like this, okay, so you have rotated it you rotate it by 90 degree. Now that same point will no longer be axial point. It will obviously be equatorial point. Earlier, it was the axis. Now the axis is this one. This obviously will be the equator. At the same distance, obviously the field will be like this, and the field will now become E by 2. Remember 1:2 ratio? On the equator, it is half or 1 as compared to 1:2 ratio basically. On equator, it is 1, then axis it is 2. On axis, it is 1, then equator, it is half. So if it is E, it is E by 2. That's it. So the answer to this question will be just C option, which is E by 2. Yeah, that's the electric field over there. Perfect. By the way, some of you might be wondering, why the hell did I mention the field like this downwards? Why not upwards? Logic goes like this. See, this is negative and this is positive charge. So if you look at the field lines, right, the field over here will go like this, right? This is how the field lines will go. Over here, the field will go like that and come back over here like this. So when you are here on the equator, it is exactly opposite to the dipole moment. That's the reason why it is shown in the opposite direction of the dipole moment. Okay, that's something which you can keep in mind. Okay, fair enough. Now let's go to another interesting question. Let's go to another interesting question, but this will be your homework question. Let's see how many of you will be able to do this. Okay, very good question. Imagine there is a dipole like this and like this. This dipole moment is P. This dipole moment is 2P. This is the origin. This is the origin. And let's say this dipole is at a coordinate of, this dipole is at a coordinate of 2r comma 0. This dipole is at a coordinate of r comma 0, or I think you can mention it opposite. This is at r comma 0 and this is at 2r comma 0. Question is, question is find find the field and potential at origin. Find the field and the potential at the origin. Beautiful question. Both the dipoles will give you some field and potential. Vector addition might be needed for field. For potential, it's just a scalar quantity. Okay, so this is a beautiful homework question to tease your brain. Okay, answer should be there in the comments. Just like before, every lecture, at the start of the lecture, I will show the names who have solved the homework. Even if you are doing it recorded, even if this session is done, please put up the answers in the homework. It will definitely tease your brain. Solutions, answer key will be there in the PDF. Okay, so answer in the comment section. Answer in the comment section. Okay, beautiful question this is. All right. Now, let us go to the next concept. See, a dipole used to create a field, a potential space around it. But what happens if you take a dipole and place it in somebody else's field? That's the next part. Yeah. What if I take a dipole and place it in somebody else's field? Crazy, right? Guru, you can also order these hoodies, by the way. It's there on the Vedantu store. The link is there in the description. A lot of cool stuff, not just hoodies, t-shirts, bags, water bottles, pencil boxes, so many things are there. Okay, so check out. So what happens if you place a dipole in somebody else's field? So there are multiple cases over here. Imagine you take a, oops, imagine you take a dipole like this, like this, this, like this. Okay, and this is positive. Oops, this is positive, 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 negative, negative, just for your understanding purpose. And let's say this is the electric field lines. The difference between these two is based on the uniformity. This is basically a uniform field, external, the yellow lines. This one is some kind of non-uniform field, some kind of non-uniform field. What happens when you take a dipole and place it in an external field? That is the concept that we are discussing. So a dipole in an external field, very, very important. A dipole in an external field, in an external electric field. That's what we are discussing. Dipole in some external field. Okay. Now, if you consider uniform field, which is a much easier case first, see, we all know that electric force is charge into the field, and the force is the direction of the field. If the charge is positive and if it is negative charge, the force is opposite to the direction of the field. Standard thing which you have learned in previous lecture. If you have missed the class, then please check it out. It is there over here. Yeah, electric field and field lines. We have discussed this in detail. Okay, sir. Fair enough. So, the positive charge will experience a force like this, a force of Q into E. This guy will experience a force of Q into E, but in this direction. Here, there will be a field which will be E, so force of QE like this. Here, there will be a force of Q into E like this. Now, if you notice in uniform field what is happening, whether this case or this case, whether the dipole is at an angle or aligned with the field, doesn't matter. These two forces are cancelling out each other. So, you can say that the net force on it is definitely a zero. Where in the case of uniform field, in the situation of uniform field, 100% I can say the net force is always going to be zero. But this force is here, this force is here. They are producing some kind of a torque. It is trying to rotate it. Here the forces are collinear. They are pulling it. It's like taking a pen and pulling it like this. It will not rotate, nor will it translate. It will just stay there. So there is no torque in this case. So in this case, the torque is zero. Here, the torque is definitely non-zero. So I can say that very clearly in an uniform field, in an uniform, in an uniform external field, a dipole, a dipole, a dipole will always experience what will it always experience? No net force, no net force, but there is a but it may, this word may is important, it may experience a torque, it may experience some kind of torque depending on the situation or the orientation of the dipole. But force will always be zero. So no net force in any situation, but it may, depending on the position, experience some kind of torque. Is this absolutely clear, everyone? But what about non-uniform? What about non-uniform fields? What happens in that situation? Let's see over here. There will be some force like this, and here the field is strong, so the force will be also much stronger. So QE1, and this will be, let's say, QE2. This is weak, this is strong. Over here, this is weak field because the field lines are far away, so the force will also be small. So Q into E maybe. Here the force will be very strong because the field is stronger, so it will be Q into E. So here you can see that obviously the forces are not cancelling. Here also forces are not cancelling. So net force is definitely not zero. But here the torque is zero. here there is a torque. Here the torque is definitely there, and here the torque is 0. So in a non-uniform field, torque may or may not be there, but net force is definitely non-zero. So in a non-uniform field, so an in a non-uniform field, in a non-uniform field, the net force is always zero. Sorry, net force is always non-zero, always non-zero. But torque may be there. But torque, but the torque which is there may be there, may be there depending on the orientation. It is zero here, it is non-zero here. Okay, that is the major difference between uniform field and a non-uniform field, as you can see. Okay, fair enough. Now, majorly we are going to study dipoles in uniform fields, although non-uniform field, you should know what can happen. It is just a vector addition of all these forces. So starting off with dipole in a uniform field. Okay, dipole in a uniform field. What will exactly happen? So let me actually not use this diagram. I'll use this diagram. Okay, so let's just. Okay. So that is the dipole moment. That is the electric field, as you can see. So let me start marking them. So our dipole moment always goes from negative charge to the positive charge, right? So dipole moment is here, okay, which is basically your P over here. Electric field, which is going to act from outside, it is like this. So that is our electric field. And the electric field with the dipole, the electric field with the dipole is making some angle. And let's say that angle which it is making is example theta. So angle which the dipole is making with the field is basically theta. Okay. I want to know what is the torque. Force I know is 0, 100%. So I'm not doing that again. Net force is going to be 0 always. Net force is always going to be 0. I just mentioned it. Net force is always 0. What about the torque? Okay. See guys, this force and this force together become a couple force. A couple force is where two equal and opposite forces act at two separate distances. So that produces a couple force or couple torque. So that couple force produces a torque which is also called as a couple torque. So you will see there is a force like this over here. There is a force like this over here. And there is also a force like this over here. Magnitude wise, if you see, it is just Q into E, magnitude wise. This is also magnitude wise Q into E. So there is 100% a torque which is there like this, a torque which is being created like this. So the net torque on the dipole, that will be the couple torque, and the couple torque is always any one force. You take any one force into the separation of those forces, any one of the forces and separation of the forces. That is the concept also there in rotation. So if you take any one of the forces, it is Q into E. So just put Q into E over here, multiplied by the separation. Now you might be wondering what the hell is the separation now. See, this force is here, this force is here. So if you ask me what is the separation between them, then I would say the separation is basically this distance. This particular distance over here, which you are seeing, that is nothing but the separation. That is nothing but the separation. Oh, okay, fine, got it. But sir, the distance between the charges is, let's say, L. From here, from here to here, whatever this distance is, that is L. If this is theta, if this is theta, think about it. Think about it. If that is theta, okay, this angle over here is also theta, and so is, or forget it like this angle, this line and this line are parallel lines. So this angle and this angle are alternate angles. So this will be also theta. Can you guys see that? Can you guys see that? Two parallel lines. This is theta. This is an intercept. So theta and theta, alternate angles. Perfect. Okay. So what will be that separation? This is hypotenuse. As you can see, sine of theta, sine of theta will be nothing but the separation divided by the hypotenuse, divided by the hypotenuse. So therefore, our separation will be the hypotenuse, which is basically the length, into nothing but sine of theta. So the separation which I'm talking about is nothing but L multiplied by sine of theta. L multiplied by sine of theta. Okay. Now I have an idea. Charge into length. Charge into length is basically the dipole moment. I can write them together. So let me write Q into L together. Let me keep E separate, and let me also keep sine theta separate. Let me also keep sine theta separate. Perfect. So that is going to give me the magnitude of my torque, and I know charge into length is the dipole moment. E is nothing but our electric field, and sine theta is just sine theta. So torque magnitude wise happens to be P into E into sine theta. P into E into sine theta. Perfect. We got the value of the torque which is experienced by a dipole inside a field. Okay. Sir, but I know dipole is a vector, E is a vector, torque is a vector, and I am also saying sine theta. That reminds me of something. Yes, vector product, cross product. So I can write torque vector is nothing but the dipole moment vector, and I can put electric field vector, and then I can put a cross product if I want to express it in the vector form. If I want to express it in the vector form. So the torque experienced by it is P cross product with E. So if P is the dipole moment, E is the electric field. Take your four fingers of the right hand first in the direction of P, slowly move it towards electric field. Then this right hand's thumb points the direction of the torque. So that means the torque is like this. That means the torque is in this direction. Absolutely clear? Yeah? Who am I? It's completely up to you, whichever you want to watch. But this one has a different set of problems as compared to the Roar series. Roar series is one shot marathon. This one is mini lectures, and the enthu and the energy for watching these lectures will be higher for you as compared to the marathon. So it's completely dependent on a personal choice and personal level. Is that okay? Cool. Then where will the unit, sir, if we take two equal and opposite charges, then where will the uniform field be? Rama, be careful that when I'm saying that the uniform field is there, it is not the field created by this charge. It is the field because of some other charge. Maybe there is a plate which has some charge that is creating electric field, and you are placing these two charges in front of that plate which is generating that field. Same thing, this field might be coming because of some other new charges. I am not talking about the field because of the dipole. Think like that. Imagine if the dipoles are generating field, how can that field itself apply the force on itself? If a charge is creating a field, that field can't act on the charge itself and push it. Then a simple charge in space will start moving. It's like I am only pushing myself. I can't push myself. Somebody else's field can apply a force. Getting my point? So that's why I mentioned external field. Do not get confused by the field generated by the dipole itself. Is that clear, everyone? Everyone? Very good. Yes, who am I? That's quite enough for your JEE Advance. Sir, Are there some special situations for these conditions? Are there some special situations for these conditions? 100%. So let's see what those special situations are. Okay, what are those special situations? Observe it carefully. First of all, this special situation where your dipole is like this, then your dipole is like this, and lastly, your dipole is like this. And in each case, the electric field is here only like this. Okay, this is your electric field, and electric field. If you ask me the angles in each situation, theta is, I mean, they are all parallel. So theta is 0, no angle, 0 degree. Here theta is 90 degree. Here they are both opposite. So theta is 180 degrees. So let's calculate the torque in every case. If you ask me in the first case, P sine theta. So sine 0 is 0. So the torque will be 0. P sine 180. Sine 180 is also 0. So the torque will be again 0. Here sine 90 is 1. So the torque will be P into E. So the torque will be nothing but P multiplied by your E. Now sine 90 is the maximum value of sine. Sine 90 is the maximum value of sine. So the torque can be maximum when sine is 1 or theta is 90. So whatever torque you are getting over here is basically the maximum torque. This torque is the least torque. You can't go magnitude wise below this. So the minimum torque is 0, maximum torque is P into E. Fair and simple. Another important thing over here is that when the torque is 0, what does it mean? You take the dipole and place it in the field. It is not rotating. It is not experiencing any torque. So it will not rotate. It will stay as it is. Here also you keep it in the external field. The dipole will not experience torque, not experience force. It will not rotate. It will stay as it is. So when it is staying as it is when kept, it means it is in equilibrium. Whereas here, it is experiencing a torque. The torque will just pull it. Okay, it will try to rotate it. So in fact, these are also cases of equilibrium. So this is actually stable equilibrium. Stable equilibrium. Stable equilibrium. Very, very important. And this is the case of unstable equilibrium. Now, some of you might have forgotten these words. What is unstable and stable? Don't worry, I understand all of that. So I'll tell you very simply. Guys. See, electric field is like this. The electric field is like this. Consider three situations. First situation, the dipole is here. Second situation, the dipole is here. Third situation, the dipole is here. Then again, take these three situations. Again, the dipole is here. Then the dipole is here. The dipole is here. Now, this is the situation of our equilibrium. Observe this. Here, the torque is 0. Here also, the torque is 0. Because here theta is 0, here theta is 180. Now, if I move the dipole slightly here, what will happen? Immediately, there will be a torque like this. Torque is P into E, P cross E. It will be like this, anti-clockwise. This torque is trying to restore it back. This was the disturbance. Theta was you disturbed it from its equilibrium. You moved it like that. The torque is pulling it back. If you disturb it like this, again, the torque is trying to pull it back. So it is always coming back to that. That means if somebody deviates you, disturbs you, you come back. If somebody disturbs you, you again come back, restore back. That means that equilibrium is very stable. If somebody moves or disturbs you, you are concentrating your focus, so you are coming back. That is the reason why when theta is 0, you are saying it is a stable equilibrium. Whereas if you consider the opposite scenario, look at it, how the torque acts. The torque acts here when you disturb it slightly this side. The dipole was facing opposite to the field. So you move it slightly here, zoop, it goes here, it moves away. So it moves away. So the disturbance was here. You disturb it in this direction. The torque pushes it away. The torque pushes it away. Same thing here. You move the dipole slightly onto this side. You will see that the torque will push it away like this. So it was on a very thin line over there. It was in equilibrium. You move it slightly here, zoop, it falls. You move it slightly here, zoop, it goes the other side. So it is unstable. It is in equilibrium only at that place. The moment you displace it, that's it. It's gone. It's not trying to come back. Okay? Okay? I hope this is absolutely, absolutely clear. Okay? Everyone with me? Aditya, my dear, please go and screw up some other channels. Don't screw up this channel over here. Why are you wasting time? I'm pretty sure you are not a student. Somebody would have sent, because recently some calls came to me, and I said no. So I know you guys are unnecessarily interested in disturbing a good channel. So why do you want to waste other people's time? I know who you guys are, right? So please don't come here. I know you are not a student. I have also got calls, and I know who you guys are. So why unnecessarily waste time? Yeah, you just want to put down a channel because I said no to you, and I want to stick over here with my students, right? Yeah. Anyways, moving up to the next question. Next concept. Yeah. So we spoke about torque, we spoke about equilibrium, and I explained you what is meaning of equilibrium. But now I get a sense of this. Like I have a compass. If I can, I don't know, or I threw it. Oops. Yes, I have a compass. Now, see guys, when I see a compass, I don't know, I somehow feel that it behaves like this dipole only. I mean, if you take the needle of the compass, okay, and you move it slightly here, north is here, zoop, it comes back. You take it here, zoop, it comes back. And I also get that feeling that as if there is some invisible spring in it. If I try to rotate it and I leave it, zoop, it will come back as if some energy was stored in it. If I take that needle and rotate it and leave it, as if there is an invisible spring, not a real spring, and it is trying to bring it back. So there is definitely energy which is in the form of stored energy, which we call as the potential energy. But this will be electrical potential energy. So the next concept is the electrical potential energy of a dipole placed in that external uniform field. That is what we are interested in. So I will again use this diagram only better. Yeah, this diagram only. So yeah. So the energy of it. Let's talk about it. Let's talk about the energy of the dipole. Now, remember one thing, whenever we talk about energy of potential energy of anything, always it is measured with respect to something, isn't it? Yes or no? Yeah. Yes, Virupaksha, teaching is more than enough for understanding concept and cracking any entrance. Yes, yes, definitely. I mean, many students, some of the students just came and told that, sir, in the mock test, I got 70 plus marks in my, coaching, just by watching your physics classes. So you can see that. And I'm pretty sure there are more 7-8 months left for your JEE mains. And by that time, you would go even better marks. Now, when we talk about potential energy, it is always measured with respect to something, some scenario, which we call as the zero reference energy. So the zero reference energy is a situation for electric dipole when the dipole is perpendicular to the electric field. Very, very important. So we assume when the dipole moment is perpendicular to the electric field, when it is perpendicular to the electric field, that means theta is 90 degrees, then we assume that the potential energy is 0 joules. Potential energy is 0 joules. This is very, very important scenario. You should know. Lot of people make this mistake. They consider energy is 0 when theta is 0. That is wrong. We define theta is 90, then energy is 0. That is my 0 reference. So as per that, when I rotate the electric dipole, I will be measuring the energies. So to measure the potential energy, the logic used is whatever, let's say I rotate the dipole by a small amount. So if I rotate the dipole by d theta, there will be definitely some external work done. The external work done goes as the change in the potential energy, a change in the potential energy. So therefore, I can say the small change in the energy is the work done by external force. That work done by external force undoubtedly will be the torque which I am applying multiplied by the small angle by which I have rotated it. Let's say it is d theta. The external torque will have to balance the torque of the dipole which is experiencing the torque by the field. So it will also be equal to P into, it will also be equal to P into your E into basically your sine theta. P into E into sine theta. So the torque which you have to apply to rotate it, it was here, I rotate it by a small angle. So it should be balancing out the torque which the dipole is experiencing because of this field. So that you are able to overcome it and move against that torque. Okay. So that is basically du. That is basically du. Now you integrate this du. P is a constant, of course. E is also a constant. And only thing which is variable is theta because I'm continuously changing the angle. And what are the limits of integration? When theta is basically 90 degrees, I move it till theta over here. The energy at 90 degrees is 0. And over here, the energy is, let's say, u. The energy is some random u at some angle theta. So what is the integration going to look like? It will become u minus 0 is equal to u minus 0 is equal to, we have over here P and also E. Integration of sine theta is negative cos theta. Integration of sine theta is negative cos theta. So minus cos theta minus cos 90. I have put the limits of it. Cos 90 is 0. Minus 0 is that same thing. So it is just going to be a negative sign with a cos theta over here. We will have u over here is equal to P into E into cos theta with a negative sign. That negative sign is very, very important for solving the questions. So let's block it. Potential energy is negative P cos theta. But I have an idea now that dipole is a vector. E is also a vector. I can see U is a scalar and there is cos. So obviously we can use dot product over here and I can write this as a negative sign, put a dot product over here and put P vector dot E vector. P vector dot E vector. That is also fair enough. So this or this, it's one and the same. So potential energy is negative P cos theta, which is also negative P dot E, which is negative P dot E. So if you go back to this diagram of stable and unstable equilibrium now, again, we can add few more things like over here. When theta is 90, I mean, come on guys, theta is 90, cos 90 is 0. It should be 0, energy is 0 and it's following this 0 reference energy concept. So 100% over here when torque is maximum, the energy is a big fat 0. What about over here? What about over here? What is the energy like? Think about it. Theta is 0. PE cos 0. Cos 0 is 1. So this negative sign carries forward. So energy is negative PE. Negative PE. If you go back and put theta as 180, which is what we need over here, where is it? Which is what we need over here. Cos 180 is negative 1, negative 1 into negative 1, positive 1. So it is plus PE. So over here, the energy is going to be plus PE. In fact, this is the maximum energy you can get. A lot of people think this is the minimum energy. Completely wrong. Negative is lesser than 0. So this is the minimum energy. 0 is not the minimum energy. That's again a crazy concept. Okay. And it kind of makes sense that at stable equilibrium, the energy should be the least, and at unstable equilibrium, the energy should be the maximum, which is exactly the case. Okay. So that is your stable, unstable equilibrium. Yeah. Saket, you can use the role series if you want one shot, marathon kind of thing. But like I said, this year, the winners will be the ones who watch daily classes, small classes, full of energy, and maintain the rhythm and the consistency rather than losing focus in a long lecture. And by the time you have reached the third hour, you have forgotten the first hour. So small dose than a big bottle full of vaccine. Yeah, that is what will decide. Okay, completely up to you. Both are good in their own way. Let's solve some questions. Okay, last few questions and the lecture is over. So given below are the two statements. A point charge is brought in a field. The value of the field at a point near the charge may be increasing, or if the charge is positive. Electric dipole is placed in a non-uniform field. The net force on the dipole will not be zero. So a point charge is brought in an electric field. The value of the field at a point near the charge may increase if the charge is positive. Well, that kind of makes sense. If you take a positive charge, the electric fields will be like this. So here it will be strong. Here it will be weak. So as you go closer, the field becomes more. Yes, that is definitely correct. Nothing wrong in that. What about this? The electric dipole is placed in a non-uniform field. The electric force will not be zero. Guys, I just explained it to you over here. If you have a non-uniform field, then the net force is always non-zero. Look at it. The forces will not be able to cancel out each other. So the second statement is also true. First is also true. So both statements are true. Option A. All right, everyone. Perfecto. Yes. Yadu, hi, welcome. Guru, last few more minutes. Okay. All right. Let's do a beautiful JEE Mains 2025 question. A beautiful JEE Mains question. Oops, I think the answer is shown by mistake. A dipole with two charges, separation is placed in such that the axis is parallel to the field and the potential difference is 5 volts. Separation between them is 0.5. The dipole is rotated by 30 degrees, tends to realign in the direction due to a torque. The value of the torque is how much? Okay. See guys, I'll tell you what. Imagine one plate here, and I tell you that there is a voltage difference of how much? 5 volts. 5 volts of voltage difference. And there is a distance between the plates also. How much it is? 0.5 millimeter. 0.5 millimeter. So that voltage difference will create an electric field like this. It will create an electric field like this. And we have seen the formula for electric field. Remember, the magnitude of the field is nothing but dV by dr. Last lecture's only concept. dV by dr, delta V by delta R. Voltage difference 5, distance 0.5 but millimeter. So 10 to the power minus 3. So this will make the magnitude of the electric field. 5 cancels. This is 10 to the power minus 4. So it will become 10 to the power 4 volts. Sorry, not volts. Volts per meter. Electric field is 10 to the power 4 SI units, which is volts per meter. Perfect. dV by dr concept I have used. I need it to find the energy. Now what has happened is, see, you have taken a dipole. If the dipole is rotated by 30 degrees from the axis, it tends to realign in the direction due to the torque. The value of the torque is. So you have kept the dipole like this. You have kept the dipole like this, and it is making 30 degrees over here. Question is, find the torque. Obviously, the value of the torque, torque, the value of the torque is P into E into sine theta. First, let's find out P now. Because the dipole moment is charge multiplied by length. Charge is 2 micro and the length is 0.5 micro. 0.5 micro. 0.5 into 2 is 1. This will become 10 to the power minus 12. So the dipole moment is 10 to the power minus 12. That is the first thing. Multiplied by what is the field which we just got? We got the field as 10 to the power 4. And lastly, we need sine nothing but 30 degrees. Sine nothing but 30 degrees. Perfect. So this will just become 10 to the power minus 8 and sine 30 is nothing but half. So if you want, you can write half as 0.5 into 10 to the power minus 8. So this will become 5 into 10 to the power minus 9, but this will be Newton meter. So that's the torque. 5 into 10 to the power minus 9 Newton meters of torque. Perfect. We got the answer. Is that okay, everyone? Absolutely clear? Yeah, D option, not C option. Okay, very good. Sir, I got 72% in 12th and no improvement exam in my state, but I want to take a drop. How is it possible that your state does not have improvement exam? It's a very weird situation. Just see if you can change your board or something. Else, don't take a drop, man. Don't risk it. Okay, don't risk it. All right. Yes, there is one more question coming up on your screen. Here it is. Two short dipoles are placed as shown. The energy of interaction between these dipoles will be. It's crazy. It's beautiful concept question. One dipole is here, another dipole is here. The distance is far. What is the energy of interaction electrically? Okay. Now, if you notice, for this particular dipole, this becomes the axis of the dipole. This becomes the axis of the dipole. And at this particular point on the axis of the dipole, the electric fields will be like this. So it's as if you have an electric field on the axis of the dipole. And this electric field becomes external for this dipole. Are you getting my point? This dipole, this is the axis. So it's going to create an electric field, which is this one at this point. And this becomes external for this P2 because E axis is created by P1. So the electric field on the axis due to P1, how much will it be? It will be K 2 times P1 divided by R cube. Remember 2 times? On the axis, the field is always 2 times more than the one on the equator. So that factor of 2 comes because you are on the axis. This is basically external field. This is basically external field for our dipole P2. External for P2. So there will be an energy, and energy will be negative, whatever this field is, external, dot producted with our dipole moment. So when I take dot product, you should always put cos theta. Okay, so this will become negative. Electric field on the axis is nothing but 2k P1 divided by R cube. Dipole moment 2, I'll just put it as it is, and then you have cos theta. So the energy of interaction is exactly this one. So minus 2k P1 P2 cos theta whole thing divided by R cube, which is option B, of course. Can you see that? Exactly option number B. Okay, beautiful question. Field due to a dipole is calculated and that field becomes external to another dipole. So we use energy is minus E dot P. Okay, that's it. Yeah, it is not B or C, it is just B. So it is sine theta versus cos theta. It is definitely not sine theta, it is cos theta. Okay, fair enough. So that was the answer, and I think that was the last one. So my dear students, if you want a dedicated batch for JEE 2026, you want the entire 11th and 12th syllabus with class tests, assignments, with the Tattva module, along with quick revisions, final one shots, all India level mock test series towards the end, and also JEE advanced preparation, along with Shreyas Sir's entire library of V-Buddy classes, and also maths and chemistry V-Buddy library, and all the books which you need for JEE, the PYQ books, the objective books, the theory books. You are going to get the digital versions of this so that you don't have to spend 1 rupee extra. Then please join the Sigma batch. The link is there in the description. It's a pure English batch under the mentorship of your Captain Shreyas and Namrata ma'am and Diksha ma'am. Okay, so your Captain Shreyas sir is there, Diksha ma'am, Namrata ma'am, along with Pahul sir, PNJ sir, who themselves are IITians. You are having them in this particular batch, and the syllabus will be completed by October-November period, where you have around 300 plus live classes, around 3 classes per day, weekend tests, and you have instant doubt solving in the class, and watching the replay also you can ask doubts. Yeah, that's beautiful. Soft copy of Tattva material, live quizzes, DPP generator apart from the regular DPPs, 500 plus ebooks, all India level test series, and a dedicated student group for your studies, discussion, and doubts. Okay, so do not forget to check it out. The link is there in the description box of today's video. Okay, so I'll just open it up and show it to you. Then in the just go down, as you can see over here, Sigma batch for JEE 2026. Yeah, perfect. And it's at an offer right now. It has just started. If you have missed it, don't worry. You can watch the replay immediately because there is no further entry point. These prices were actually supposed to go up. I'm surprised it has not changed. I'll just change it. Okay, I'll ask the admin team. Okay, it has to, or maybe it's an error. It will go up immediately. Okay, so make sure you are in this particular batch as soon as possible. In this batch, you have 3 versions. One is the Prime Sigma batch. Here you get quick revision cards, hard copy, small flash cards for your revision for physics, chemistry, maths. Here you get the Tattva books hard copy. Some people prefer it. Okay, it's completely up to you. All right. Thank you so much. If you've forgotten to like the video, please like it. Yeah, do that right now and comment the answer of the homework question. Okay, homework question. I'll just show it to you again in case you have forgotten. Yeah, this is the homework question. So post the answer of the homework question in the comments. See you guys. Bye bye. Take care. Have a great time.